we can calculate the amount of heat that is needed to change the temperature of something. And the equation is right here. Q equals mc delta T. And that's an equation that you need to memorize. Q equals mc delta T. Q equals MCAT. MCAT is a test that you need to take to get into medical school. This delta is not an A, but it kind of looks like an A. So this looks like MCAT, right? So Q is the amount of heat measured in joules. M is the mass of the substance in grams. C is the specific heat capacity in joules per gram degree Celsius. And delta T is the temperature change. So this triangle is the Greek letter delta. It's a capital delta. And we use that in science to represent change in. And we almost always do final minus initial. And the sign here is sometimes important. So delta T is always the final temperature minus the initial temperature. So if you had an ice cube at 0 degrees Celsius and you turn it into boiling water at 100 degrees Celsius, the change in temperature is the 100 minus 0 or plus 100 degrees Celsius. It went up in temperature, the delta T is positive. If something gets colder, then the delta T is negative. And if we look at what happens with the units, see if I can squeeze it in here in the bottom. Q is in joules, M is in grams, C is in joules per gram degrees Celsius, and delta T is in degrees Celsius. The units all work out, because the Celsius would cancel the Celsius, the grams would cancel the grams, I end up with joules equals joules. So the units work out. This is an equation, and you can solve these problems thinking in terms of algebra and using the equation. But because of the units on specific heat capacity, it really suggests to you what you should do. And so if you forget the equation, you can use the units and just combine the numbers so the units work out and you can come up with the right answer that way. So let's do an example. This one has a lot of words in it. You find a copper penny, pre-1982, in the snow and pick it up. How much heat is absorbed by the penny as it warms from the temperature of the snow, minus 5 degrees Celsius, to the temperature of your body, 37.0 degrees Celsius? Assume the penny is pure copper and has a mass of 3.10 grams. You can find the heat capacity of copper in table 3.4. Well, let's go find that. And by the way, this page numbers like this, these are from the 4th edition. I need to update these, but it's not going to happen this semester. So let's go back and find that. Copper, heat capacity, 0.385. So the symbol for heat capacity is C, 0.385, and the units were joules over grams degrees Celsius. Always write your fractional units vertically. Okay, so lots and lots of words in here. Let's look at the numbers. Here we've got a minus 5 degrees Celsius. We have a 37 degrees Celsius. We've got 310 grams. Let's write those down. There's 37 and minus 5 and 3.10 grams. This number, 3.10, is a mass, right? It says mass of, but the unit gram also tells us that is the mass. We have two temperatures. Let's think about what's happening. I'm picking up a cold penny, and when I put it in my hand, it's going to warm up. If I hold that penny long enough, it will become the same temperature as my hand. So what was the initial temperature of the penny? -5. So this is T sub I for initial temperature. And what's the final temperature? The 37 degrees. It warms from the temperature of the snow, -5, to the temperature of your body, 37. So we need to identify initial and final. What's the question? What are we trying to find? How much heat? There's an equation for that. Q equals mc delta T. Q is what we're trying to find. Don't ask me why they use Q for heat. I think they used H for too many things and they ran out of letters. So Q, I don't know. M is mass. Do we know that? Yep. Do we know C? Do we have delta T written down? No, but could we figure it out? Yeah. So I'm just going to do it down here out of the way. Delta T equals the final temperature minus the initial temperature. So the final is 37.0 degrees Celsius minus the initial. So be careful with those minuses. So that ends up being 42, right? So delta T equals 42. Now, should I put 0.0? I'm subtracting here. This has 1 decimal place, and this has 1 decimal place. The result of that subtraction should have 1 decimal place. So this should be 42.0 degrees Celsius. So now I can take those numbers, 3.10 grams times 0.385 joules per gram degrees Celsius times 42.0 degrees Celsius. There's not enough room here. 3.1 times 0.385 times 42. How many significant figures should my answer have? It should have 3. This number has 3 sig figs. These specific heat capacities are not exact. They are measured. And my temperature has 3. So it's going to be 50.1. And what's the unit? Joules. And when things are really messy like that, a box around the answer is really helpful. The grams canceled and the degrees Celsius canceled. Any questions? A lead fishing weight with a mass of 75 grams absorbs 146 calories of heat. If its initial temperature is 47 degrees Celsius, what is its final temperature? What kind of an equation are we going to use to solve this? That MCAT thing, right? MC delta T? Are we going to need to look anything up? We probably need the specific heat capacity of lead. A lead fishing weight. That's the element lead. So I'm going to go back and look that up before I start writing stuff down. 0.128. So the specific heat capacity for that is 0.128 joules per gram degrees Celsius. Now you might think to look that up later, but if I start writing and then I have to go back, then I lose everything I wrote, and I don't want to do that. So we've got numbers in here, right? Identify the numbers. 75 grams, 146 calories of heat. We have the 47 degrees Celsius. Good approach is just to write those down. 75 grams, 146 calories, and 47 degrees Celsius. Which one of those is the mass? And what letter should I give 146 calories? Q. That's heat. Calorie is a unit of energy. And this temperature, is that a final temperature, an initial temperature, or a change? That's initial. And we know that because it actually says it's initial temperature. So I pulled the numbers out and I just labeled them. What are we trying to find? What is its final temperature? Well, what equation have we used? Q equals mc delta T. Now, does that directly have T final in it? No, it doesn't. Now, depending on your level of ability with algebra, you could sub in there the quantity T final minus T initial and solve for T final and do it that way. But you can do that without me showing you how, so I'm not going to do that. So for the rest of us, we know what Q is, we know what M is, and we know what C is. Could we solve for delta T? We could. And if we know delta T and we have the initial temperature, could we figure out the final temperature? Yeah, we could. So let's do it that way. So let's rearrange this equation for delta T. So we're going to look at, there's no fractions here. So here's delta T. We want him by himself. We look at the other guys that are with him. We've got mass and specific heat capacity, and they're multiplied. We want to do the opposite. The opposite of multiplication is division. So we're going to divide by mass and divide by specific heat capacity. Mass over mass is 1. C over C is 1. They go away. But I have to do the same thing to both sides. So I'm going to get M and C over there. So now I have delta T equals Q over MC. So I can put in my numbers, 146 calories, and my mass is 75 grams, and my specific heat capacity is 0.128 joules per gram degrees Celsius. This is an example of why you need to write the units every time. Is there a problem with these units? These grams are going to cancel. We've got 1 over degrees Celsius, so that guy will pop up into the numerator and be fine. But are the calories and joules going to cancel each other out? No, it's not the same unit. We need to convert. So there's two options here. We could take Q by itself and convert it to joules and then plug that in here. Or we can put a conversion factor right on top of, right next to this equation and take care of it that way. Which way do you want to do it? Separately or all together? Separately, okay. We'll do it separately. So I'm going to take this guy, I wish he was on the bottom. Oh well, I'm going to do him up here. So 146 calories. You see that? Yeah. I want to convert that to joules. So I need joules on top and calories on the bottom, so the calories will cancel out. This is dimensional analysis. Is it 1 calorie to 4.184 joules or 1 joule to 4.184 calories? It's one calorie is 4.184 joules. So I've got 146 times 4.184. That's going to be 610 point, didn't leave enough space, 864 joules. I don't want to round that number yet. I want to keep extra sig figs so I don't get rounding errors. How many significant figures should that number have? 3. My 146 has 3, and this one has 4. So this is limited to 3. So I'm going to underline the third digit so I remember that only has 3 sig figs. So now, down here, I'm going to erase this number and sub in my converted Q so that the units are going to work out. So that's 610 underlined, 0.864 joules. Now the joules cancel. So,
I have trouble with why we couldn't. What is the 0.18?
the 0.128?
Yeah, that's the lead, right?
This is because it's lead, the specific heat capacity of lead. We looked it up in a table.
Yeah.
Okay? So when I rearrange the equation, I end up dividing by the mass and dividing by C. And so that's why the mass and C end up being in the bottom. Okay, good question. So 610.864 divided by 75. Be careful here. Divided by 0.128. Do this one on your calculator. I'm serious. Do it and make sure that you come up with the same answer. So delta T then is equal to 63.63166, repeating. These just go sixes forever. And that would have the unit of degrees Celsius. The common mistake that students have is they'll end up with 1.0425. If you get 1.0425, you're having a calculator issue, and we can talk about that right after lecture. It's going to come up again and again, and it's not going to go away. Students see that 75 times 0.128. If you insist on multiplying those, you need to put parentheses around the outside. Otherwise, you end up with a different number. So this is the change in temperature. How do I find the final temperature? Well, the safest thing is to say, well, delta T is equal to T final minus T initial. So then if I rearrange that equation, I'm going to end up with T final being equal to delta T plus the initial temperature. And I've really run out of space there. So 63.631 and a bunch of sixes. Then I'm going to add 47. Plus 47 equals I can kind of sneak it this way. So T final equals delta T plus 47. And my calculator is showing me 110.631666667. How many significant figures should this number have? That came from this mess. This had 3. This had 3. This had 2. So this number has 3 sig figs, just the 63. So I'm taking 63 with an uncertainty of plus or minus 1, and I'm adding 47, which also is in the ones place. So I should have my final answer will round to 111 degrees Fahrenheit. Any questions? Oh, Celsius. Thank you. Just seeing if you're awake. Any questions? This is a more challenging question. The most straightforward ones are the ones like I did in the first one, where they give you MC and delta T, or the things that you can very easily combine to get them, ask you to calculate Q. This is about the hardest one we'll do, because we're looking for T final, which is part of delta T, and there's a unit conversion thrown in there as well.
Wait, how did you get the 111?
The 111, I took this, this equation, delta T is the final minus the initial, and I rearranged it. I added Ti to both sides. So the final temperature equals the delta T plus the initial temperature. And I was out of space, so I moved up here. The final temperature equals delta T plus the initial 47. Any other questions? My question is, how many slides are left? Oh my goodness. Okay, we're not going to do that last one. We'll do this one, and then we'll call it a day. When 56 joules of heat are added to 11 grams of a liquid, its temperature rises from 10.4 degrees Celsius to 12.7 degrees Celsius. What is the heat capacity of the liquid? Well, we got some words and some numbers. Let's pay attention to the numbers. We'll find them all in here. We'll write them down. We'll label them. 56 joules, 11 grams, 10.4 degrees Celsius, 12.7 degrees Celsius. $11 grams is what? The mass. So that's M. And here we got the temperature rising from 10.4 to 12.7. So 10.4 is the initial temperature, and 12.7 is the final. And then 56 joules, what letter does that get? That's the heat. That's Q. And they are asking, what is the heat capacity? What's the letter that we're using for heat capacity? C. So we've got that equation, Q equals MC delta T. That's kind of in the way. I need to rearrange this and solve for C. So I'm going to divide by M, so those guys go away. And I'm going to divide by delta T, so they cancel out. And then I have to do the same thing to the other side, because you got to keep things equal. And that's kind of messy to look at, so I'm going to copy it over with the C on the left side. C equals Q over M delta T. Delta T equals the final minus the initial. The final is 12.7. The initial is 10.4. So that ends up being 2.3, right? We're subtracting 1 decimal place, 1 decimal place, and so our answer should have 1 decimal place. So we're going to put Q in, 56 joules. we're going to put in the mass of 11 grams and the change in temperature of 2.3 degrees Celsius. And we're going to do this on our calculator. 56 divided by 11 divided by 2.3 equals... How many sig figs should the answer have? 2. All these numbers have 2 sig figs. So 2.2, and the units are joules per gram degrees Celsius. Because none of these units cancel out. Joules, grams, degrees Celsius, they all stay there. And that's why the specific heat capacity has such weird units. Any questions? Yes? Okay, that's a good question. Why did I divide by 2.3 instead of multiplying? So let's look at that. Come on. I'm trying to get a... Oh, I did. Okay. We need a clear screen here. Okay, so if we take... let's use letters instead. If I have... A divided by B times C. That is not the same as A times, oh wait, where am I going with this? What can happen on your calculator is you can end up with A times, A divided by B times C. So let's put some numbers in there. Let's put in 12 and 3 and 6. Now on your calculator, 12 divided by 3, you go 12 divided by 3. When I press times, my calculator does the division. So when I press times, my calculator has finished that and gives me 4. If I multiply by 6, then I get 26. No. 24. Because that's doing this, 12 over 4 times 6. On my calculator, 12 divided by 3, and the next sign that I press, times or divide, it finishes this. I want 4 divided by 6. And so I need to go divided by 6, and I'll get 0.67. If you really want to multiply, and for some people, this is just this big, doesn't make sense to you thing. So if you really want to multiply those, you need to go 12 divided by parentheses 3 times 6, close parentheses, equals. So do it on your calculator. Make sure you can come up with 0.67 instead of 24. This is a common problem when we're dividing by two numbers that are multiplied by each other. Any other questions?
So could you just times 3 times 6 and then multiply?
There's a variety of things you could do. You could take 3 times 6 equals, and then do 1 over, and multiply by the top. That works. There's more steps. I need more space. I'll erase that again. I think it's best to think of this. Let's stay with that same example. 3 times 6. That is the same as 12 over 3 times 1 over 6. Do you agree with that? Because when you multiply fractions, you multiply the numerators, you multiply the denominators. So I'm just separating these guys out so that I don't have multiple terms in the bottom. This is like what we did in dimensional analysis where we have fractions and you go times the top, divide by the bottom, times the top, divide by the bottom. Well, timesing by 1 doesn't matter. I'm dividing by 6. This is how I think of it and how I would recommend that you learn to think about it. But if you want to use parentheses and multiply in the bottom, you are welcome to do that. Just make sure you always use the parentheses. I really don't recommend writing down intermediate values. You could take this and do the 3 times 6 and write down, okay, that's 18, and then I've got 12 divided by 18. But every time you write something down and then take that and put it into your calculator, you have 2 opportunities to make mistakes. Because sometimes we transpose digits, right? Or we push the wrong button on the calculator. And so we want to minimize those errors. So if you have something like this, where a number on the top and numbers multiplied in the bottom, think of it pulled apart this way. It's 12 divided by 3, skip the times 1, divided by 6. Any other questions? And if you want me to talk to you more about that, I'd be happy to. Then at the end here is chapter in review, which can be helpful for studying. And we finished it